let's start, and I'm starting to record. So this is homework number 12, number 11. So in homework 12, number 11, I was supposed to get a chance to look at part D, but I didn't. So let me look at it again. So we have the centralizer. So we have G, a group. The centralizer.
Would you be able to reposition the page and the cable so that we can see everything?
Okay, let me see if this makes a difference. In video.
Thank you.
Okay. Okay, so G is a group, X is an element of G, and the centralizer C of X is everything in the group that commutes with X. So all G in G such that GX G inverse equals X, which is the same as saying all G in G such that G times X is X times G. So that is the centralizer. And we want to show there is a one-to-one correspondence between the left cosets of the centralizer and the elements of the conjugacy class of X. So why is that? So we have the left cosets, G modulo the centralizer. So this is everything of the form G C of X for G in the group. And we also have the conjugacy class of X, which is gamma of X, which is everything in the group that you can write as the form GX G inverse for some G in G. So to every element of the conjugacy class, I want to assign a left coset and conversely. Okay, so we take a Y in the conjugacy class and we associate that to the left coset Y times C of X. So this is a map from the conjugacy class to the left cosets. And I would like to show, because this is sort of an obvious map, let's see if this is one-to-one and if it's one-to-one and onto. So suppose we take another Z in gamma of X, and let's see, so Z goes to the conjugacy class Z C of X. So what can we say? If Y C of X equals Z C of X, that happens if and only if Z inverse Y is in C of X. So, so that happens if and only if Z inverse Y X equals X, Z inverse Y. Which is the same as saying Z inverse Y X times Z inverse Y inverse is equal to X, which is the same as saying that Z inverse Y is in the centralizer. So I invented this problem. So I'm trying to figure out what I was thinking at the time and why I'm having a problem with this. So we want a one-to-one correspondence between the conjugates of X and the left cosets. So if I take something in the conjugacy class, I send it to YC of X. Now, so I have no idea. I'm going to think about this some more because I haven't thought about it since this morning. And I don't understand what I was, how I got this. So I will say, we'll figure out.
So, Professor, but can you actually at least explain what the question D was asking? Because I kind of didn't even understand what sort of relationship we were trying to establish.
Well, so we have a group G. We have a subgroup, the centralizer of this element X, and we have the left cosets, G mod C of X. So this is the set of all left cosets.
Yeah, so far so good. Yeah.
Okay. And we also have the conjugacy class of X, which is the set gamma of X, which is all conjugates of X. So this is a subset of the group. And the claim is that there is a bijection, a one-to-one and onto function from the set of left cosets and the conjugacy class. And the number of left cosets, we just call that the index of the subgroup in the group. So that's going to be equal to the cardinality of this conjugacy class. That's what we're asked to prove, assuming that it's true.
So can I rephrase it using numbers? Let's say G has a cardinality of 10 and centralizer of X has a cardinality of 2. Then you expect 5 left cosets.
Yep.
And then the group gamma of, not the group, but the set gamma of X will also have only 5 members. Is that what we're basically trying to say?
Correct. Well, yeah,
okay.
That's just, yeah, sure.
I had few other questions. This was one of my questions. If anybody else is waiting, they can go before me. Otherwise, I can start.
Just one quick one. Thank you very much. Professor, homework 11, question 6, please.
Homework 11, question 6. Okay, so homework 11, number 6. So we have, so there are 4 parts. In part A, we have a function. So R times, this is the non-zero real numbers, positive and negative, but not zero. And we can define the function f of x to be equal to x squared. So this is a homomorphism because f of xy is xy squared, but for real numbers, that's x squared y squared, which is f of x times f of y. So it's a homomorphism, but it's not one-to-one because f of 1 and f of minus 1 both get sent to the same number 1. And it's not onto because f of x equal x squared equals minus 1 has no solution. So in the reals, there's no square root of minus 1. So the function's not onto, and x and minus x all get sent to the same thing. So it's not one-to-one.
Professor, I'm sorry to interrupt for a second. In this case, it's not one-to-one and it's not onto, but we only need to show technically that one of those conditions does not exist. Is that correct?
No, because the problem says, show that is neither one-to-one nor onto.
Okay. But just missing one of those would make it a homomorphism. Is that correct?
It's a homomorphism regardless. This
Okay.
means it's a homomorphism.
Okay, thank you.
All right. So in all cases, this is a homomorphism. Now in part B, we're going from the non-zero reals to the positive reals. And this function is onto because if x is greater than 0, the square root of x exists. And f of the square root of x is square root of x squared is x. So this function is onto, but again, it's not one-to-one because 1 and negative 1, for example, get sent to the same number. So if I look at the function, the square function from the non-zero reals to the positive reals, that's onto, but not one-to-one. If I go from the positive reals to all the reals, non-zero reals, squaring, it's not onto because nothing gets sent to a negative. The square of a real number is never negative, but it is one-to-one. Because if you look at the squaring function for the positive numbers, it's strictly increasing. It's one-to-one. And if you look at this function from the positive numbers to the positive numbers, this is an isomorphism. It's a homomorphism that's one-to-one and onto. So that's what it is.
Thank you.
So if I can go, I'm having a slightly hard time with the first theorem of the isomorphism.
Yep.
And my confusion stems from the fact that we are starting with a homomorphism, which is F. And then we are basically proving that it, or we are given that it's onto. And then one of the steps says that because it involves kernel of F, it is also one-to-one. I don't see that connection. So I'm trying to figure out that, how do we go from homomorphism to isomorphism? And how is that onto and kernel make it one-to-one?
Okay, so suppose we have G from G prime, a homomorphism. So there's a simple fact that F is 1-to-1 if and only if the kernel of F consists just of the identity. Okay? And the proof is as follows. So we know for any homomorphism, F of the identity is the identity, right? If you're going from G to G prime,
Yeah, so far so good.
the identity gets mapped to the identity.
So
So,
far so good, yep.
so if F is 1-to-1, then E is the only element in G, the only element X in G, such that F of X equals E. If you had another element going to E, the function wouldn't be 1-to-1. So therefore, if F is 1-to-1, the kernel is just the identity.
Okay, yeah.
Okay.
So far I'm following it.
Conversely, if the kernel, so suppose the kernel is just the identity. If X and Y are in the group and F of X equals F of Y, then F of X, Y inverse, this is F of X, F of Y inverse is F of X inverse is the identity, which would imply that X, Y inverse is in the kernel, which is just the identity, which means X, Y inverse is the identity, which means X equals Y. So a function, a homomorphism is 1-to-1 if and only if its kernel is the identity. There's nothing to do with onto anywhere, but 1-to-1 is equivalent to the kernel of the homomorphism being equal to the identity.
Okay, so in the first theorem of the isomorphism, we are going from left cosets of G to G prime, and because the kernel is the set subgroup H itself, which is considered identity, it becomes isomorphism. Is that basically the logic?
Well, so we have a homomorphism from G to a group G prime. And I proved that if H is any normal subgroup of the kernel of this homomorphism, which I'll call K, then you can map G to G mod H. That's just the canonical homomorphism. And there is a homomorphism F tilde from these left cosets to G prime, such that F is equal to F tilde times composed with pi.
Right.
All right. Now, if we choose H to be equal to K, then we have G going to G prime. This goes into G mod K, and so we have F, pi, and F tilde. And
so if I can say it, then F, because that implies F tilde is also homomorphic. And
well, we know F
because-
tilde is a homomorphism. That's part of this basic little theorem.
Right. And it's onto, and now it has a kernel which is mapped to identity. That's what makes it isomorphic.
Right. So the kernel of F tilde is all the cosets xk such that F tilde of xk is equal to the identity in G prime.
Right.
So
Which
that's
is
the
H
same
itself.
as all x, so, but f tilde, so this is all xk, such that f tilde pi of x is equal to the identity. So, let's see. What do I want to say? Sorry. So, so this map f tilde is always 1-to-1. That was part of the theorem. So,
Right.
So this is 1-to-1, and if G is onto, if F is onto, then this is also onto. That's really all there is to do.
No. So, I mean, that was the part that I was struggling with, that, you know, the F tilde is 1-to-1 and we don't start with that. So that, I think that's what you were basically showing me in the previous example, that if it's onto and if
Well,
the kernel is identity,
So forget
then it becomes
onto for the
1-to-1.
moment. We have G going to G prime with some homomorphism F. We have K is the kernel of F. That's a normal subgroup of G. And we have H, a normal subgroup also of G, contained in the kernel. So this is normal subgroup of G. So we have a map from G to G mod H, and I claim there's a map F tilde from G mod H to F. So I would define F tilde of a coset XH to be F of X. And the question is this well defined? So suppose XH equals YH. Does it follow that, see, so if XH equals YH, we would have F tilde of XH is F of X, but X to H is YH, so this is F tilde of YH. So this has to be equal to Y, F of Y. So does it follow that F of X equals F of Y? And the answer is yes. Why is that true? Because F of X equals F of Y if and only if X inverse Y is in the kernel of F, which is equal to K, and what am I saying down here? Sorry. If XH equals YH, that means that X inverse Y is in H, which is contained in K, which means F of X equals F of Y. That's all we need to say. If XH equals YH, if these two cosets are equal, that means X inverse Y is in H, but H is contained in K. So that means F of X inverse Y is the identity, or F of X equals F of Y. So this function is well defined.
So well defined means 1-to-1?
No, well defined doesn't mean 1-to-1. It means that there's no ambiguity. See, here I defined a coset. F tilde of XH is F of X. But there's nothing unique about this X. The coset XH can be equal to the coset YH for different values, for different elements X and Y. Right? You can have XH equals YH. X and Y don't have to be the same.
Understood.
But for this function to be well defined, it must be the case that F of X equals F of Y. And that follows because H is contained in the kernel.
So how would you sort of describe well defined? Because that's something that I'm not very clear about. I mean, we have used it for quite some time, but I was never very clear about it.
Well, it means that there's no, let's see, so what's an example? Suppose I take the integers mod 4, and I want to define a function from the integers mod 4 to some group. I want to define some F tilde. So, and I want to define it How? Well, the problem is, if I take a coset 3 plus 4, 7 plus 4z, that's the same as the coset 23 plus 4z. They're the same coset. But if I define the function in terms of this number, then it has to somehow give me the same thing whether I use 3 as the representative element of the coset or 23 as the representative element of the coset. No matter which representative I use to describe the coset, f tilde has to give me the same value. So here I have a coset xh, it's here, and I want to define f tilde of that. So I say that f tilde of xh be equal to f of x. But I can have two different numbers, two different elements of the group x and y here, different, but xh equals yh. So I have to know in that case that f of x still equals f of y. And because h is contained in the kernel, that is the case.
Okay. Now I understand that. Thank you. So to continue with that theorem though, the function f tilde is well defined, but how do we show that it's 1-to-1 too as well?
Okay,
Or is this a proof?
No. So here is a proof, right here. I'm about to write it down. So suppose f of xh, you take two cosets, xh and yh, and suppose f tilde of xh equals f tilde of yh. That means that f of x equals f of y, because that's what the f tilde of xh is f of x, f tilde of yh is f of y. That means that x inverse y is in the kernel. Sorry, this should be a k. It's 1-to-1 when h is equal to k. It's not 1-to-1 in general.
Mm-hmm.
So that means x inverse y is in the kernel. That means, in fact, these cosets are the same.
Okay,
So
yes.
if you have the kernel, then this function is 1-to-1.
Okay, now I understand it. Thank you. So I wanted to clarify a few things especially for the exam. So in the exam, let's say a question says that, prove that this set or XYZ is a group. So do we have to show all four conditions, which is closure, identity, inverse, and associativity, or can we just simply prove that for all x and y, x inverse y is in the set?
If you want to prove something as a subgroup,
No, group.
then you have to prove everything.
You have to prove everything. Okay.
Right.
So only for
First of all,
subgroup I can prove x
you have to
inverse
say
y
that
is
x inverse y makes sense. So that means you're showing that your set is closed under multiplication. I mean, you
Okay.
can't talk about x inverse y if you don't know that you have a binary operation on the set.
Okay. So for group, we have to show all four. For subgroup, we can just show x inverse y to show that it's a subgroup. And if we can also show that, hx, h inverse belongs to that subgroup, then it's also normal. No, the other way, x, h, x inverse, right?
Yeah. For all x.
For all x. And those are only for subgroups, though, not for groups.
Well, you can't talk about normal. There's no such thing as a normal group.
Right.
A subgroup
No.
of a group may or may not be normal.
Understood. Another question in terms of proofs, Professor. In the midterm, there was a question, I think question 4, that was basically the theorem 2.11 in the textbook. So if we have a question like that, do we still have to sort of rewrite it, because it's basically a copy and paste job at that time?
I have to read the proof and think that it's okay. It's if it's a valid proof, it's a valid proof.
Because I mean, the reason I'm asking is in midterm, it was literally one of the theorems, I think 2.11 or something. That's what it was asking.
I'd have to go back and look and see what you wrote down.
Okay. No, I'm talking about the finals tomorrow. Let's say there's a question that's literally a theorem from your textbook or your notes. Do we still sort of have to prove it? Because that would be simply just copying from your notes.
If I say to prove a theorem, then you have to prove the theorem,
Okay.
no matter where the proof comes from.
Okay.
Just a reminder, before Rebecca had left, they had requested that we do number 3 from homework 12.
Okay, just 1 second. Yeah, okay. So,
Well, I think, yes, that question seems to be wrong, I think.
we'll see. So homework 12, number 3. So if I take a matrix A0, 0B, and I conjugate it, by a matrix, I'll call it RSTU. So what is that? So this multiplies the first column by T, and it multiplies the second column, sorry, by B. And if I,
Professor, I actually did the same thing, and
yeah, no, just a second, that's all right. So this multiplies the first row by A, and the second row by B. So it's not a normal subgroup. So what I should have said is just the diagonal subgroup. So not normal. And what I should have said is that HB, the set of diagonal matrices with the same number down the diagonal. So this is normal. Right.
But isn't that just a A times I identity, basically?
Yeah, of course. But it is a subgroup. It's a normal subgroup.
Right.
It's not the identity. It's all scalar multiples of the identity.
Scalar multiples for it, right? I don't know if you already did this, but homework 12 question 7 and 8. Is there any easier way to do that other than just list out everything and do it? Because for S3 there are 6 elements, but for S4 it may be much worse.
Well, so I did it this morning, but let me just repeat the general idea. If you have a cycle in a symmetric group and you conjugate it by a permutation sigma, you get the cycle sigma of A1, sigma of A2, sigma of AK. So when you conjugate a K cycle, it goes to another K cycle. And conversely, if you have any two K cycles, there's always a permutation sigma. So if you conjugate this, you get this.
Right.
And what that says is that, so now you take any permutation in Sn. And you can write it as a product of k cycles, or a product of cycles. One of length k1, k2, up to k sub r, where the sum of the k's
Is n.
is equal to n. And so every permutation is a product of disjoint k cycles. So, and two permutations are congruent if and only if you have the same number of k cycles and the same lengths adding up to n. So for example, if you look at S4, you just have to ask, how can you write 4 as a sum of positive numbers? You have 4 equals 4, 4 equals 3 plus 1, 4 equals 2 plus 2, 4 equals 2 plus 1 plus 1, and 4 equals 1 plus 1 plus 1 plus 1. So there are 4 ways to write down 4 as a sum of positive integers. And that means 5 ways. So that means there are exactly 5 conjugacy classes. All the 4 cycles, whatever they might be, are in one class. All the 3 cycles are in another. All the permutations, which are products of 2 different transpositions, are in a class. All of the just the transpositions by themselves, and this is just the identity. So in S4, there are exactly 5 conjugacy classes, and this describes them completely. The 4 cycles, the 3 cycles, the 2 cycles, the identity, and the permutations that are products of 2 disjoint transpositions.
So each of this conjugacy class will not have the same cardinality then?
Conjugacy classes do not have to have the same cardinality, absolutely not.
Right. It's only for the left cosets and right cosets.
I don't know what you mean by that, but conjugacy classes do not have to have the same number of elements. Different
Okay.
conjugacy classes in a group have different cardinalities in general.
Okay.
The only time they have all have the same cardinality is when the group is abelian and each conjugacy class has exactly 1 element.
I think that was a is that the sort of part of the last question, the 12E
Yes.
or 11E?
No, it was part of what was a mistaken problem. What was number 6 in the original version of these of this homework, where it said prove that a group consists of 1 conjugacy class if and only if the group is abelian, and the right statement is that a group of order n has exactly n conjugacy classes. That is, each conjugacy class has a single element if and only if the group is abelian. Oops. Just 1 second, please.
So in S4, how many different 4 cycles will be there? 6?
I'm sorry, there was just a comment that I missed.
No, I was asking in S4, how many 4 cycles will be there? Will it be 6?
How many 4 cycles?
Mm-hmm.
Well, I think so. Of course, you can start with 1 And then in all the different ways you can permute 2, 3, and 4, there are 3 factorial ways, which is 6.
Right. And would that form a cyclical group or no? Because yesterday I was looking at like sigma square and sigma cube, etc., and one of them
So the
became
set of 4
2
cycles is not a group. It's just a set.
It's just a set. Okay.
Yeah, conjugacy class is not a group. It's not a subgroup.
It's not a subgroup. Okay.
I mean, each 4 cycle generates a cyclic group of order 4, but that's something different.
So can you repeat what the question 6 should have said? It says prove that a group consists of one conjugacy class if and only if the group is abelian.
Oh, so it should say something like a group is abelian if and only if every conjugacy class has exactly 1 element.